Hi, welcome back, everyone. Our next speaker is Paul Zsamboki, who will talk about simplicial commutative bundles. Thanks, Paul. Go ahead.
Thanks for the invitation. So as you can see, this is joint work with OK, and the preprint is on the archive, so you can read it. So this is basically a project about trying to transpose the notion of transitionally commutative bundles from the topological case to the simplicial case. And there's going to be two parts to the talk. First of all, I'm going to talk about the generalization we did in the topological case, and then I'm going to talk about how we try to mimic what happens on the topological case to do the same in the simplicial one. So the first part is going to be about the topological case. So I'm going to talk about topological simplicial bundles. Wait, topological principal bundles. With tau structure. So, and the first thing I'm going to do is to recall. Wait, I can do this fancy. Do it. Okay. So the first thing I'm going to do is to recall how the simplicial nerve of a group looks like. That being the nicest way to remember how the construction of the topological classifying space looks like. And it's also going to be a key construction in our generalizations. So, you know, this works as follows. So you take at first a discrete group. And then there's two steps. So in step one, you can view it as a category. So its object set is just one point, and the set of morphisms of that point is G, and then composition is multiplication. So if you've got two entries, G and H, then the composite is just GH. And then so now that we are equipped with this category C, we can take the simplicial nerve and C. So, you know, the point is that the n simplices are given by n tuples from G. And then the point is that why I wanted to recall this thing is that the face and degeneracy maps are just the ones you need for BG. So of course, you know, if you look at the n simplices, then NC, so the n simplices are just d to power n, but then the simplicial maps are easy to describe. So, you know, if you want to look at di of this thing, then if I is 0, you just leave out the first guy. If I is between 1 and n minus 1, then you just compose gi and gi plus 1 and leave the others the same. And then on the other end, you just forget in. And on the other end, you're just forgetting the other G. And then the other thing I'll be using is that, so, the point is that this is for discrete groups, but you can do the same stuff for topological groups or simplicial groups. And basically to put it really shortly, you just take the homotopical colimit afterwards. So, and then the other thing you can do is that you can have a similar construction for the universal principal bundle. Then you can take the groupoid G tilde, where the object set is G, and then for two entries GH in G, the Ham set is a singleton. So, okay, so this is a singleton, so it's not too exciting. The point is how I'm writing these up, because that's gonna give us, in an easy way, the simplicial structure on the universal bundle. So, and then again, how you take composites is that you've got H1 going from G to GH1, you've got H2 going from GH1 to GH1H2, and then you just compose. And then you can here to take the simplicial nerve, and then, so now the n simplices are given by n+1 entries from G. And again, the point is that the simplicial, if you just look at the simplicial structure maps in the nerve, that can give you in an easy way the simplicial structure maps of the simplicial space, the hocolim of which is the universal bundle. So to go on then quickly recall how everything works in the topological case. Let's just recall BG like this. And then I'll move on to our generalization. Now if G is a topological group, then you can let, basically you take the simplicial space BG just to be n of G as I was talking about it. But then this is on simplices, these are just powers of G. So because of this, you can give a bit of topology. And then, okay, so okay, yeah, so we know this. So the geometric realization of this thing is BG. And then the geometric realization of the universal bundle is the geometric, yeah. So now you can do the same, where by EG, you denote this and G tilde. I just wanted to recall this because we're gonna basically generalize it in a somewhat straightforward way. And then there's the classical theorem that this thing classifies principal G bundles. So if you take a CW complex X, then this thing is isomorphic to H. All right, I mean, so far so good. Just wanted to very quickly summarize this before we move on to the generalization. So why we talk about tau structures instead of transitionally commutative structure is that that's a slight generalization. That's going to include all the other descending central series and also the mod P versions. Let's talk about tau structure. And then that's going to lead us to generalized classifying space B tau G. So how we start out is that we take an endofunctor. on the category of groups tau. And then it's got one key property that we needed to make our theorems work. And this key property is that we assume that it is of quotient type. By which we mean that there's a natural transformation from the identity functor on the category of groups to this endofunctor tau. And then for all three groups, of a finite number of generators, we want this eta to be a surjective map. So this is what we'll need for our theorems to work. And then, so let's just mention the important examples. So okay, so first of all, this includes tau not doing anything. So you can have tau just be the identity functor, which is gonna lead us just to BG. And then this also includes the transitionally commutative version. So you can make tau to be the abelization functor. Then this setup is going to spit out the classifying space BZG. And then this also includes other entries in the descending central series. And then also the descending central series with the mod P version. So, this includes all these. So let me just move on to constructing our space. So how this works is that, okay, instead of just writing up the definition, I'm just gonna say it in a little fancier way. So the nerve functor is represented by the co-simplicial group F, where it sends the free group on n generators, and then I cannot write up the simplicial set maps again if I just say this. And then, so if you're equipped with a endofunctor tau, then you can just get a co-simplicial group out of tau. And then now if you want to construct this thing, you go the same thing you do with Z. So now if we've got the topological group G, then since we are equipped with that natural transformation, so we've got this map from F to tau. So this thing gives us injections from tau into F, but that's just dg. And then so we're gonna let this be the simplicial space be tau g. And then just like in the z case and the bg case, this means that we can define the tau g to be the geometric realization of this simplicial space. And then our first result is that this thing has the same sort of classification property than the Z version. But for that, we need to generalize transitionally commutative bundles to bundles with a tau structure. So just to very quickly recall that. So if we've got a principal G bundle, then we assume that we're given a trivialization U which means that if you look at the inclusions of these open subsets, then you get a Cartesian diagram like this, where your top map is equivariant. And then, so given these beta I for all I, we can get a map, the geometric realization of which is going to be the classifying for the principal bundle. So we can look at the n term of the Czech complex on U. And then if you take x from ui0 intersect uin, then you can send that to the two-pole given by the transition maps. So thus you land in BG. So these are the maps which I can just denote by row bullet. These are the maps, geometric realization of which is the classifying map. And so to get the generalization of a transitionally commutative atlas, we can say that we want this map to factor through our object. So if there's a factorization like this, if there's such a thing, then we're going to say that we're dealing with a tau atlas. And this is the notion with which we want to generalize the classification result for commutative structure. So just to first recall the one in the Z case that, so the other notion we've got is that instead of looking at the factorization on the atlas level, we can look at factorization on the homotopy class level. So we're going to say that the bundle I has a tau structure if the classifying map, if the class of the classifying map leads to a map in this homotopy class. And you can remark that this is a direct generalization of a commutative, transitionally commutative structure. So the point is that we could make the theorem also hold in this generality. So let's first recall the older result. That, where am I? That if G is, so this is Adam Gomez. That if G is a Lie group, then in our notation, phi has a tau atlas. So pi has a Z atlas if and only if it has a tau structure. And the point is that we could make the same thing work for our more general tau, which is of quotient type. So our first theorem is that if G is tau good, which means that this simplicial space B tau G is good, then, and moreover, if the base space is a CW complex, I think it was V or X, then having a tau atlas is equivalent to having a tau structure. So this was the topological case. And yeah, any questions so far?
Can you recall us what you mean by good?
Yeah, sorry, it's a technical condition as far as I remember it. I mean, when I used it to say that the geometric realization is a homotopy co-limit. So I think it's some technical condition that lets you, lets you do what you want to do. So it's good.
Okay.
Yeah. Any more questions? So this was the topological space, and we set out to try to do something similar in the simplicial case. So this is why I recall the simplicial nerve, because, well, you just say that you have homotopy co-limits of simplicial objects of simplicial set, so you just try to do the same stuff. So this is going to be part 2, where we're going to talk about the construction of a simplicial set and how much of this property it still satisfies. I mean, what a sort of similar property it satisfies. So we're going to construct the simplicial set W bar tau k, and then say what it can do. So from now on, K is going to be a simplicial group. And so again, so just like in the topological case, you basically form simplicial objects using the nerve. So to fix notation, we can form the bisimplicial sets and K and then tilde K. You know, so here we think of K as a simplicial category, and we think of K tilde as a simplicial groupoid, and then we use component-wise simplicial nerves to get bisimplicial sets. So to say which axis is which, what we're gonna say is that, so, okay, so you know now, I wanna say what the PQ simplices are of this bisimplicial set NK. And what we're gonna say is that these are gonna be P simplices in the group KQ. So that's the convention we choose. And then, you know, so, and then just like in the topological case, you can say that this is the same as Hom F P K Q. And then once again, you can take a subobject, be given that tau is of quotient type, so you are equipped with this thing. You can look at this subobject. So this is gonna give us the bisimplicial set and tau k. And then so as far as constructing the object goes, you can now say that, cool, so I've got a bisimplicial set, I'm gonna take the homotopical co-limit and that's gonna be my object. Then of course you're like, okay, but how does it work? So let's talk about that. So basically the point is gonna be that your first try is to use the W bar construction, but then it turns out that that thing does not have enough classifying maps. So we'll actually need to use something else in the end. So, okay, so once again, what we say is that basically we want to study the hoponym of this. And so basically we need to pick our model for the homotopical co-limit. And then so the first try is to take the total simplicial set. So just to very quickly recall how that works. So there's a map called the décalage, which makes a bisimplicial set out of a simplicial set. It basically breaks the simplices in two. So the so basically, if you take a simplicial set X, then the PQ simplices of the décalage are just the P plus Q plus 1 simplices in X. I'm not going to say any more before time constraints. But you know, the idea is really just that you take the p plus q plus 1 simplices, and then you instead look at p simplices on one axis and q simplices on the other axis, and then you only look at those simplicial maps which do that for you. And then this is just a nice way to get the total simplicial set functor, because there's just the right adjoint of this thing. And you can prove that if you're given a bisimplicial set, then Tx is a model for the homotopic then. So what you can do is that you've got your bisimplicial set and apply this functor T to it, and you got an object and you want to study it. And then why we started out with this approach is that if you're looking at tau being just the identity functor, then this works. So we've got our map of bisimplicial set, nk tilde nk. We just throw t at it. And then this is wk, this is w bar k, and it's a theorem of May that this is a universal principal K bundle. And then we're like, nice. So now we just need to take our classifying maps and say when those are tau atlases, and then we'll be very happy. So it's going to turn out that this approach is not going to work, but we're going to be using the notation used to define regular atlases anyway. So I'm just going to recall them anyway. And it's also just nice to see how this doesn't work. So let's just recall regular atlases on a simplicial principal bundle. So as far as atlases go, that's going to work similarly than in the topological case. So it's nicest. And then I'm still going to follow May's approach. Just start with fiber bundles. So if you're looking at fiber F, then if you want to show if you've got a map of simplicial set and you want to give it a local trivialization, then what you want is for each simplex of the base simplicial set B, you want to have a Cartesian diagram of this form. So this is going to be denoted by beta B. So this is a local trivialization. And if you're given one such thing for all n and for all n simplex in B, then you've got yourself an atlas in the simplicial setting. And for fiber bundles, I'm going to say soon how this is going to get us principal bundle atlases. But first, there's an important construction. So basically how you can get transition maps in the simplicial setting. So the important point here is that you've got the mapping simplicial, the endomorphism simplicial set of F, and the automorphism simplicial group, of course, has a right action on it. And then the important proposition is that local trivializations over a given simplex are an art F and torsor. And then you can use this to get your transition maps, because now what you can do, so this is notation, is that suppose that you are also given a map of ordinals theta, and then the transition map is going to be the map that goes between two ways of getting out of beta B local trivialization over the pullback of B. So you know, if you've got, what am I doing? Probably, I'm just going to follow my notes. So if you've got beta B here, then you can just pre-compose with identity cross the map defined by this. So if you just pre-compose, then you're gonna get the pullback by theta of beta B. But another thing you can do is just to pre-compose down here, and given an atlas, you just take the local trivialization over this map. So that's gonna be beta theta pullback B. And then because of that torsor property, sorry, I'm gonna put this on the other side. There's gonna be an element of the automorphism simplicial group that's going between the two. So this is gonna be sitting in FM. And then so we can use these transition maps to say when is an atlas regular. So basically, you'll want it to be trivial with respect to as many simplicial structure maps as possible. So what you can say is that the atlas beta is normalized if this transition map is trivial for all degeneracy maps. And then we say that this atlas B is regular if furthermore this transition map is trivial for all face maps but one. And then so to give the classification result, I just wanted to recall one last definition that, so, you know, you've got a K action on F if you've got a subsimplicial group K of F. And then you just say that tau is a K atlas. And all these transition maps sit in K. And then now we can say how to explicitly get classification maps for our principal bundles. You know, this is going to be important because similarly to the topological space, you actually wanted to know how the atlas looks like so that you can say when is it a tau atlas. So the proposition here is that, so this is still in May, that, so you're given a simplicial principal K bundle. And then first of all, it's gonna has a regular atlas. And then second of all, that regular atlas is gonna give you the classifying map by a formula. So it gives the classifying map. And then the good point here is that why it's nice to study is that you can actually write that thing down because we're going to use the adjointness between decalage and total simplicial set, and you can just write down the map from the decalage. So if you've got a PQ simplex of the decalage, so that was just a P plus Q plus 1 simplex in B. And then you can just map it to this thing that you do D0 P minus 1 alpha star, B D0, blah, blah, B D0, etc. Alpha star D0 to P minus 1 B D0. And then, you know, so that's going to land in the PQ simplices of NK. And then you use the total simplicial set functor and you get the classifying map. So you actually have a formula for it. And then so we were hoping that, you know, you can just say when it's a regular atlas, a tau atlas. But the problem is that the tau structure may not be given on a regular atlas. So the point is that this is nice, but we need some other object which has classifying maps coming from non-regular atlases. So once again, why this is not good for tau is that the tau structure might be on a non-regular atlas. And then also another reason why it's difficult to deal with is that this set is not, this simplicial set is not vibrant. Which makes it more difficult to study its homotopy theory. So we constructed a different simplicial set. It was still not vibrant, but we conjectured that its classifying maps can be given by atlases and even non-regular atlases. So this gets us to the other model we considered, which is the nerve of the Grothendieck construction. So I not have time to say much about the construction, but you know, the point is that by grotadic construction, I mean the co-end. So what I mean is that a simplicial set is a pre-sheaf. So you can take its co-end to get a fibered category. And similarly, a simplicial groupoid you can think of as a pseudo-functor. So you can take the co-end of that too. So what we can do is that B is a simplicial set. So it's a pre-sheaf. So you can take its co-end, which is going to be a fibered category over delta. And then, so how you can write this down is that, I guess I not have time for that. So, I mean, it's got a nice simple definition. And then similarly, your simplicial group K, you can think of as a pseudo-functor. So that 2 can be given a co-end. And then similarly, you can have, so these are fiber categories. And then these are big enough that for any atlas, I get a map between these objects. So now I can just construct given an atlas, beta, we can just construct a functor between these fibered categories. And then you can take the nerves of these fibered categories. And then so now, so you know, basically the point is that we're going to construct a subsimplicial set of this, but first I'm going to just state the main theorem and the conjecture corresponding to it. So the point is that this construction has the correct homotopy type. First, I'm going to say a tau thing, which I haven't defined yet, just so that I can do things in order. So another theorem is that there's a zigzag of weak equivalences between n tau k. So just as in the other case, this is going to be a subsimplicial set of this n integral k. And the other object we started with. So this construction also gives us the correct homotopy type, but we just at this point, we can only conjecture that actually this alpha I defined is a classifying map. So our conjecture is that, so since there's a natural, so the zigzag of weak equivalences is natural in tau and k. So now what you can do is that along this thing, so you know, since there's a natural weak equivalence, so you can look at this homotopy type, And then there's a bijection between that and this homotopy type. And to show that we've actually got classifying maps, we want to show that here we've got the class of that map alpha star we have defined. And then on the other side, we've got the classifying map coming out of the regular atlas I recalled. And the conjecture is that this bijection between the two takes one to the other. So, you know, that would mean that the map we have defined is a classifying map. So I'm out of time, so I just wanted to very quickly mention the generalization of that theorem about the correspondence between tau structure and tau atlases. So I not have time to define the notions, but I just wanna indicate it. So we can use this variety, this version, and tau, co, and k. We can define tau atlas. And then, so just on the nose, we managed to prove that if we have a tau atlas, you know, which means that all map alpha star I defined factors through this thing. If you have a tau atlas, then you have a tau structure, which is a factorization in the homotopy category. But we couldn't get the other way with this. So we needed to weaken the notion of tau atlas. To weak tau atlas, which basically means to go over the topological side. Since you've got the nice result in the topological side, there from a tau atlas, you get the tau structure, and then you can port the tau structure back to the simplicial side of things. And then we could show that, as in another proposition, that if you have a weak tau atlas, then you get, wait, no, if you have a tau structure, then you have a weak tau atlas. And then to finish, let me just mention that this also uses two theorems we've shown, which shows that our object is compatible with the topological side. So to finish, let me mention these two results. So, you know, you take the simplicial group, you can take a geometric realization, which gets you a topological group. Then you can look at the tau classifying space of the topological group. And then we have shown that this topological space is the same as the geometrical realization of the simplicial, the geometrical realization of the simplicial object. And then there's also a similar result that if G is a compact Lie group, then the object B tau G can also be gotten as the geometrical realization of W bar tau as G. So the takeaway of this is that it was easy to construct a simplicial object which has the same homotopy type as the topological object, but to port the classification result over to the simplicial side, you need to work more. But we have shown that using this conjecture, which says that there's an object with classifying maps, non-regular atlases, we can also take over the full classification result to the simplicial side. Thank you.
All right. Let's thank the speaker. Thanks, Paul. We still have time for one quick question, I think. Does anybody want to ask a question? If so, just unmute yourselves and ask.
I have a question. Do you have any other examples of tau structures that do not arise from descending central series, or basically quotienting out by commutators?
Jihan, do we?
Okay. Let me think. Well, yeah. As you know, these are the main examples, but maybe something like a p-adic completion might be. I'm not sure if that falls into the definition that we want the tau structure to be quotient type. I think like you can replace the integers with p-adics, right? With that, yeah. Maybe you can take like a colimit of these quotients of descending central series, right? Something like that. But yeah, but I mean, the main examples are the ones that Paul talked about. Yeah, I haven't really thought about any different, essentially different tau structures. So yeah, we haven't looked at anyways.
Okay, thanks.
In your paper with Sihan, you make a point of having to get around the problem when something is not regular. What is it that goes wrong when it's not regular?
I'm sorry, I couldn't clearly understand the question.
Okay, let me try again. And if it's still not clear, I'll put it in the chat. In your paper with Sihan, you worry about the covering not being regular. And I can't quite comprehend the non-regularity. What is it that would go wrong if it's not regular?
So for regularity, we needed that, we needed all those DIs to be 1, and we needed all those degeneracy maps to be trivial. But the point is that when we have a tau like the issue is that you can have a tau atlas and you can have a non-tau atlas at the same time. So you can't be sure that the tau atlas you find will happen to be regular.
What goes wrong if they're not regular?
You just don't get classifying maps to W bar K. You only get classified. So, the classifying map is gonna be a different atlas. So you lose the tau structure when you look at the homotopy type. You look in the homotopy category, but the only classifying map you know of is coming from a regular atlas.
Huh, okay.
So you can't see the tau structure from the regular atlas. So this is why you need a different classifying space, which gets you classifying maps coming from non-regular atlases, because this might have a tau structure and this may not have a tau structure.
Oh, okay. Curious. Thank you.
Right. So I think we don't have time for any more questions, but people are free to ask more questions during the discussion session. I will in particular. And maybe now, so that we don't have the next talk immediately, 2-minute break. And if anybody comes in right now expecting the next talk, I'll just tell them it'll start in 2 minutes.
That's fine.
All right. Thanks, everyone.